This week we are going to spend some time in this area, organic chemistry, and on Friday we are going to finish the week with one lesson on the elements, where you find them in the earth, how you take them out of the earth, how you process them into products. It's a very generic lesson that we are going to have on Friday, but it's going to give you an idea of all the industry that is around chemistry that so far we have not touched at all. Next week, a couple of lessons on electrochemistry and one final exercise on Friday the 13th, or Friday yes, it's going to be Friday the 13th, which is something recalls us some nice movies, I think. And then I am going to deliver the very last lesson of the theory part on Wednesday, the week after. It's going to be the 18th. I hope that you are still here, you have not gone back to your countries. It's going to be a last lesson taped. And it's going to be on the chemistry of art, something very nice, I think, less scientific, but not completely out of science, because you will learn how mankind have used the chemical compounds to produce artworks. It's a way to live us in a very pleasant way, I think. Okay, so organic chemistry today and tomorrow, and then a last lesson on the elements and how to process the elements in the industry, and then next week electrochemistry. On Monday next week, you're going to have the guys, the assistant professor, preparing you for the practical exercise in the laboratories, describing to you in advance the experiments you will practice with your hands. This is going to help you to be straight to the point and avoid drinking things that are inappropriate for drinking and things like that, okay? So this describes you what is going to happen until the end of the year. At the beginning of next year, I will only deliver corrections in front of you of exams, which will allow me to go back to some theoretical part to provide justification for the replies. I think this is the best way to embrace, to hug everything we have done in the theory, because when you solve one of the exams, you touch a lot of points. That will be a good arena for joining every knowledge. Meanwhile, you are going to study, and you will be more and more exercise, and I hope you will give a good performance in the first written examination. That is the most critical part of the exam. Passing the written examination is the most critical, and you need the theory to pass it. It's not just like putting crosses here and there. You need to know chemistry, otherwise you don't pass it. So this is what is going to happen now until the end of the course. Fine. Organic chemistry and polymers, they are related. You may see organic chemistry as a part of chemistry that deals with the compounds of carbon, hydrogen, oxygen, nitrogen, and some other compounds. Why we call it organic? Well, in English, organic means something natural. Because it resembles what the living organisms have created. The living beings on Earth are basically made of these elements. So we may build a lot of things with these elements. They all are encompassed in the organic chemistry. Some of the things that mankind can build are things that no living beings could build. Maybe that they are even toxic. They are carcinogenic. Dioxins. Have you heard about dioxins? They are organic compounds, but they are against life in a way. But they are made of these compounds. So organic chemistry is broader than natural things. It's also synthetic things. but it's based on these elements. There is a sort of border, very precise border between what is organic and inorganic in chemistry. And you see that the properties of organic and inorganic compounds are several times very different. For instance, the inorganic compounds, let's talk about oxides, halides, these are organic compounds, metals as they are based on ionic or covalent polar bonds. On the other end, organic compounds have sort of pure covalent bonds. Sometimes they are polar, but the most frequently encountered bonds, like the carbon-carbon bonds or the carbon-hydrogen bonds, are almost non-polar, because the electronegativity, we will see that later, is either the same or very close. Second point, the inorganic compounds are soluble in polar solvents. The reason why is that they dissociate into ions. This is something we have seen in the past lesson. On the other hand, the organic compounds are soluble in non-polar solvents, and they do not dissociate. Well, there are exceptions. For instance, the acids, like the acetic acid, that is an organic compound, carbon, hydrogen, oxygen. It dissociates. It's a weak acid which partially dissociates. This is something we know. We also know that sugar, glucose, brute formula is this one, is soluble in water, which is a polar solvent, okay? The reason why is that it has a number of hydroxyl groups that are polar and are compatible with the water, so they can be dissolved. But it's not splitting, it's not dissociating. Glucose is soluble. You do that as we saw last time. Every time you have a coffee with sugar in it, but it does not dissociate. So what is written here is very generic and may have some exceptions. The inorganic compounds are often ionic solids, and the organic compounds are molecular solids. What does this mean? That you have molecules, sugar molecules, that build up networks with bonds between molecule and molecule and fixed position, so that you may have a crystal of sugar. But in that crystal, you once again do not have ions, you have molecules, like in a crystal of water, which is ice. Due to the fact that the ionic forces, the electrostatic forces that are characteristic of ionic compounds are stronger than the intermolecular forces that take place in the organic crystals, the organic compounds have lower melting points. This is something that we experience. When you have olive oil, it melts at very low temperatures. When you have butter, it melts a bit higher. When you have sugar, well, it melts, but it's also pyrolyzing. It provides this brown color, that is the caramel. So in that case, you have a sort of softening and fusion of the solid crystals, but you have also some pyrolysis, which means that it provides some cracking and formation of carbon aromatic rings that are giving you that color, and also some peculiar taste. The density, this is important. If you have a swimming pool of oil and you drop into that swimming pool of oil, you go down. because the density of oil is always below the density of water, 1 kilogram, by the way, per liter. Organic compounds have low density. What is the reason for this? Well, carbon is only 12 as an atomic weight, only 12. Then hydrogen is only 1. You may have 1. They are piling up in structures, molecules that are rather large, or they are occupying a lot of space. They are branching, they are linear. You will see this when we are going to talk about polymers. They have low intermolecular forces compared, for instance, to water, where you have oxygen that rules as a 16 as a weight, and you have hydrogen bonds, so they are going also to stay closer because they are more strongly bonded. At the end of the story, an organic compound, whatever it is, olive oil, glycerine, or a solvent like trialine, is characterized by a lower density than water because of those reasons. Lower intrinsic molecular weight of the unique formulas and lower intermolecular bonds than water. You know that the hydrogen bond is one of the strongest intermolecular bonds, but it occurs only with water, ammonia, hydrogen sulfide, and that's it. Thermal stability, when you have a crystal of sodium chloride, it is going to stay there at several hundred degrees. The people that do make pizza, you have to learn this, put some of these crystals of salt in the oven in order to have the pizza staying a bit farther away, just a bit from the bottom that is very hot, and may get your pizza burnt. It looks great above. If you do that, which is something that my wife does very often, to check, because the kids shouldn't have the carbon because it's dangerous. Well, the secret is to put some of the salt there. It helps to avoid this. There is one point. Chlorine at high temperatures and organic stuff, like the pizza, the pasta that is made of flour, is made of organic stuff, is dangerous because it may form the dioxins. So when you do that, when you put the salt over your meat, for instance, meanwhile cooking it, you are at the risk of generating some dioxins, and you do that. Because, as you know, chemistry is pushed by statistics, and something happens always. It's not going to be detrimental or tragic, but it's better to put salt over your meat after you have been cooking it, not on hot surfaces, because the reaction of chlorine with organic stuff in an oxidizing environment will give you the formation of dioxins that I will just recall as a structural formula. Dioxins are like this. This comes from the carbon parts of the meat. It's based on proteins meat. You know, it's full of carbon or hydrogen. There is also some nitrogen. It pyrolyzes, this forms a bit of carbon. Carbon is a sequence, you have learned how graphite is made, is a sequence of aromatic rings, layers. It's something like that. Oxygen comes from the atmosphere. Chlorine comes from the salt. So, but we live only once, and we have to enjoy the good pizza, and this is the way to do that. So you get a bit of this. Or the barbecue. Also, the barbecue is heavy stuff. Heavy stuff. Okay. The salt is stable until several hundred degrees. There is no organic compounds that survives 250, 300 degrees. Maybe something like 300 degrees, okay, some diatherm oil, something very tailored with a lot of chlorine inside, can withstand 300, 350 degrees Celsius. but no more than that, because pyrolysis or oxidation combustion are going to prevail above those temperatures. If you are in air, it burns. If you are not under air, and this is quite unusual in normal operating conditions, it is going nonetheless to pyrolyze, to form these aromatic rings, polycondensed, and form the benzene, the naphthalene, the anthracene, and then you end up with carbon. So it does not melt, it just changes, transforms itself, undergoes a reaction. It's not stable. Inorganic compounds are not fuels, with some exceptions. Metals can burn with oxygen if they are pure metals. But if you have a salt, you cannot have a significant amount of oxidation so as to have a combustion, because a combustion is an oxidation accompanied by a large generation of heat and a large generation also of radiation, light. This is a sort of definition of flame of combustion. On the other end, wherever you have carbon, hydrogen, then they want to become thermodynamically, in the presence of oxygen, they want to become CO2 and water. Clear? And so, if they have any occasion like a light, a sparkle or a flame, they burn very easily. Okay. So we are now dealing with carbon, hydrogen, but when you see how can these elements generate, you see with these molecules are all with only 4 atoms of carbon, 1 atom of oxygen, and as many hydrogen atoms are needed to finish, to saturate every bond available. With only 4 atoms of carbon and 1 of oxygen, you can generate as many molecules as you see there. So we are entering a world that is nearly infinite of possibilities, of molecules. The organic chemistry is by far the branch of chemistry with more compounds inside. Our body is full of very complex molecules, very complex enzymes, included hundreds or thousands of atoms in a single molecule, being it chlorophyll. I'm not a plant, so it's not in my body, or maybe in my stomach, but this is another story. Or hemoglobin, that's not so big, but you have so many different amino acids, DNA, you know. It's a very long molecule. So you may have an enormous amount of different molecules, also with the same brute formula. And this is what I told you before. To generate these molecules, you mostly rely upon carbon-carbon bonds to generate the snake, and carbon-hydrogen bond to generate, I would say, the feathers around the snake, which becomes a sort of a bird. And sometimes some carbon-oxygen bond, which is typical of alcohols, of aldehydes, of carboxylic acids, like acetic acid. But these are the most popular bonds available. The first two of them, have nearly zero electronegativity difference. The first one is 0 by definition, because it's a homopolar covalent. The second one, you see, it's very close to 0, because hydrogen is 2.1. It's very close to carbon. No? As for carbon-oxygen, you have some polarity, and this brings about the possibility to interact. It's generally the most active part of the molecule, the part where you have the oxygens, where you have more polarity. It's the part that can interact with polar solvents, for instance. It can also be the site where a reaction it can start more easily. Here you see that the arrangement of this molecule can be varied. You can have branches, side streams, starting from a mainstream. What is important to notice is that, we have already told this, a single bond may rotate. So the two parts of the molecule that are bonded through a single bond between carbon and carbon can shift, can rotate. And so this gives the molecule a degree of freedom. Sometimes when it interacts with a surface, it can accommodate itself in the best way to meet the surface configuration and stay closer to the surface. There are different ways to write a molecule, an organic molecule. The first one is called expanded formula, where you put every single bond visible. In the condensed formula, some bonds are not visible because they are belonging to groups. This is called the methyl group. Methyl group. It's a more condensed way, and you basically are condensing. I mean, you are not displaying the carbon-hydrogen bonds. You are only putting into evidence the carbon-carbon bonds that are those constituting the skeleton. Sometimes you may just write the skeleton without writing the carbon or hydrogen symbols. If you want to be more precise, and you are going to use the ball and stick or the space filling model. The space filling model we have already seen is the more realistic because it depicts the orbitals, which in case of carbon and of hydrogen, it's a 1s orbital, so it's a sphere. In the case of carbon, it's also based on the overlapping of spheres, maybe with also, if you have single bonds, it's okay like that. If you have double or triple bonds, there is not only the sigma bond, but there are also the Greek pi bonds around. But in these cases, we are only considering single bonds everywhere. We will call these kind of compounds alkanes, as we will see later on. The possibility to rearrange, like in a game, like in a puzzle, the carbon atoms in these molecules in many different ways can give you a lot of compositional or constitutional isomers. The isomers are different compounds with the same brute formula, which means with the same number of carbon, hydrogen, and, if available, oxygen. But in this page, you have only isomers of two compounds, C4H10 and C5H12. The first ones are C4. The last three are C5H12. You see that any of these three arrangement molecules have the same brute formula. But they are different, they look different, and they behave differently. You see here some properties. The density is going this direction. It is a very slight change, but it is perceivable. Also, the boiling point is going this direction. Now you are sufficiently talented, or I would say you have learned enough to understand why these trends are displayed. What is the reason why this molecule has a larger density than this molecule? Of course, I will say something funny. I will use the equivalence with the noodle soup for the first one, and with a soup of meatballs, I don't know, something spherical. Or, well, when I was a kid, I used to have also my little babies to have this kind of very small pasta to put in the soup. I hated it. I was like a sprinkler sometimes because I didn't like things in my mouth that were not very soft. And so I started spraying everything very often. Anyway, let's go back to something serious. The noodles, long molecules, are touching one another in several points. And this is essential to have London forces. Non-permanent but occasional dipoles that are the only way to have intermolecular forces. If you have a molecule like the one we see at the bottom with a lot of branches, it is going to form a sort of sphere. It is going to minimize the occasions for touching other molecules. And only if you touch another molecule you may experience a bond, even if it is weak. Even if it is weak, like a London dispersion force. So the longer are the spaghetti, the noodles, the higher are the interaction, like snakes that are touching each other into a pot. You don't have to lie to smile because you are eating this in China, I think, as well. No, I don't know. We use the snakes of we eat the snakes of the water. I mean, how do the herrings? I think is the name. They are, after all, they are also snakes. Did you understand? Okay. So if you, this is the reason why the density in this case is larger than in this case. Okay. The effect of these intensified forces of the for the first molecule compared to the last one is more evident here, where you have the boiling point. The boiling point is the temperature required to have a boiling process. So, the more intensive interaction between molecule and molecule provide the first normal pentane molecule with a higher boiling point than the last one. The difference is significant. It's something that can be easily assessed. It's 17 degrees more or less. Not bad. But now we know why this happens. Also, in this case, you have C4. Let me just polish a bit and concentrate on these two, this one and this one. In this case, you have only 4 atoms of carbon, so the molecules are smaller. But once again, the second one is a bit more spherical, so it touches less easily the other molecules. The spaghetti-like is the first one. The spaghetti-like molecules are the normal molecules, where everything, there are no branches at all. Normal ethane is obvious because there are only 2, it cannot be elsewhere. Normal propane, normal butane, which is this one, with 5 normal pentane. Now you see the difference minus 0.5 and minus 11, which is something different from before. It's now under 0. So what does this mean? That they are normally gas. These are gases. You have to go to the mountain to see them condensed. On the other end, these ones are around room temperature as a boiling point. So the first one, you may see a liquid with a very high volatility in any case. It doesn't boil but at 25 degrees, but it's not so far from boiling, which means that normal pentane likes to fly away from your bottle. It's going to evaporate rather fast. Okay? So no surprise if you take one atom out of that and you obtain the C4, it is a lighter molecule. It escapes more easily. So there is no surprise that the temperatures are lower for the boiling process because they like to become a gas, go in the gas phase much more. And no surprise that this one is higher than this one because of the interactions that are stronger. Let's move on. We have seen the cases of isomers for the C4 and the C5. Two isomers, the C4, these ones, and three isomers, the C5, the last three rows of the previous table. If you add more and more carbon atoms, you generate molecules with a larger and larger number of carbon atoms, and the isomers explode in number, become so many. Look at this number. It is 3, 3, 3. It's 4 giga, or 4, because we are a bit electronic oriented. Anyway, 4 billions of isomers when you have 30 atoms of carbon. This gives you an idea of how many molecules can be. And we are only talking about carbon and hydrogen. No oxygen, no cycles, no aromatic rings. But there are also geometric isomers. If you remember, we have already seen exactly these isomers here when we were talking about sp2 hybridization. Remember? sp2 is the hybridization of carbon where you have one p orbital of the original ones that is not hybridized. So you have 3 hybridized orbitals in a plane, and you have an original p orbital there, ready to do what? Ready to hug another one from the next carbon and build up a Greek pi bond, which is this one. In this case, when you have a double bond, the big novelty is that you cannot rotate. And so you block what is attached to the other free, the other 2 hybridized orbitals of carbon. They cannot shift position. So think of the case of dichloroethane. To be more precise, these 2 molecules have to be addressed as 1,2-dichloroethane, because 1 chlorine is attached to the carbon number 1 and 1 chlorine to the carbon number 2 in both cases. There is one case that is not represented here where both chlorines can go and stay on the same carbon atom. It could be it is the 1,1-dichloroethane. That is not considered in this. Now, you may have the chlorine atoms on the same side of the double bond, and this condition is called cis. Or you may have them at opposite sides. And this condition is called trans. Well, no surprise then, these two molecules that have exactly the same formula. You see that the formula is the same. This one and this one are the same, the brute formula, have different properties. In this case, the polarity of the carbon-chlorine bond, chlorine is much more electronegative, so there is a strong polarity, is compensating the polarity of the other carbon-chlorine bond. One is going this way, and the other is going this way. They are compensating each other, and globally it is it has no polarity as a molecule. In this case, the two polarities, let me use a different color, blue, are going this direction and this direction. They are building up an overall dipole with a positive part here and a negative part here. Chlorine is electronegative, recalls electrons, and the hydrogen is electropositive, gives them away. Okay? So basically it's going this way. The fact that this is apolar and this is polar provides different properties. When you have polar compounds, the interaction between the single polar molecules are stronger because you have electrostatic forces that overlap the London ones, and they are stronger. Even without polarity changes, you may have geometrical isomers. In this case, the difference is in the location of two methyl groups. This is called cis-2-butene, and this is called trans-2-butene. What is the meaning of this number 2? Well, it tells you where the ene, means the double bond, is located. Is it the first one of the, let me go back. Is this the first one of the skeleton bonds, the second or the third one? The second. The double bond is in between, cis-2-butene. 2 means that the second bit of the skeleton bonds, this is clear, this is only the skeleton, this only tells you what are the bonds between carbon and carbon. It tells you the second of these bonds is a double bond. It is cis or trans, depending on the fact that the two methyl groups are on the same size, cis, on the opposite side, trans, of the double bond. Also in this case, you have different behaviors. You have different boiling points. Fine? Another example is this one, dichlorobenzene. Benzene is this one, is the aromatic ring. Dichloro means you have two chlorine atoms that got substituted to hydrogen atoms. They may be close, and in this case you use the O, which means ortho. We see another example later, but it is ortho. In this case, you have, they jump one of the possibilities. They are on the first and the third of the carbon atoms. Then you have the meta. In that third case, they are at opposite carbon atoms of the ring, and this is called para. You just need P, M, or O to denote this. Same brute formula, different isomers, different properties. These are called geometric isomers. Bene, let's move on and say something about the way the organic molecules do react. In one page, you have the equivalent of an entire course of organic chemistry if you have to become a chemist. I have to simplify a lot here, and I just give you an idea of the way things are reacting. To become a good organic chemist, you need to study a lot, but then you have the possibility, starting from carbon, hydrogen, nitrogen, to build up, like in a Lego or magnet things that now are more popular than Lego, anything you want. Organic chemistry can produce a lot of different things on demand, are very close to what is the nanotechnology nowadays. The only weak point to organic chemistry is you're building very nice things, but they can burn and they are easily deactivated also by sunlight. So you may do very nice things, but the weak point is always like that. The Achilles heel is that they are weak, because unfortunately they are only made of carbon and hydrogen, and these are easy to degrade. Anyway, one thing that is used by organic chemists to produce things different from the original ones is the addition reaction. You may create a double bond. This happens if you treat at high temperature. If you have an alkane and you have two hydrogens, this is a chain and these are two hydrogens. It's very easy for these two hydrogens to go away like hydrogen and leave a double bond. This happens when you heat up pyrolysis. Ethylene can be produced this way. When you have a double bond, you may add to it a lot of different things and produce alcohols, aldehydes, a lot of the amines, a lot of different things. You put X and Y, and they are going to go here and there. You open the bond, you have two arms that can shake hands with different, and you produce different things. This is called the addition. You have a double bond, you break it, and you attach to it two parts of the added molecule. Of course, the elimination is the reverse. So you have two molecules, or two elements attached to close carbon atoms. They can be taken away and you create a double bond. This is addition and elimination. Another option is the substitution. You may add one element, pulling out another one. This is called substitution. Another option is the oxidation reduction. And in this case, you generally are attaching oxygen or attaching hydrogen, generally. A combustion is an oxidation reaction that I told you has a very high exothermicity, and this is not good for chemistry, but it's good for energy. Basically, when you burn oil, you get a lot of heat, and this is why the engines are producing their mechanical power, because the heat expands things, and the expansion translates into mechanical energy. Okay, this is a glance of the things that can be done, but there are so many different things and so many other reactions that I cannot touch in this course. The different families of hydrocarbons, of compounds of only carbon and hydrogen, hydrocarbon means that, are here represented. You may have open chain or closed rings. Linear or branched are open. When you have a snake that bites its tail, you build up rings. And believe me, this is exactly the way a ring is formed. You start from a large molecule. Due to the vibration, the tail touches one of the, this is not very, touches one of the, touches one of the carbon atoms, and they are eliminating hydrogen, and they build up a bond. You know how it works? It works like this. You cannot understand why, but you have something like this. You know that here is a carbon, here is a carbon, here is a carbon, here is a carbon. And maybe more than that. What happens more easily is that the number 1 touches the number 5. And you build up, because of this touching this, a bond and a first cycle that is this, with the rest of the molecule that does like that. Step after, you go to 6. Step after, maybe you lose some hydrogen, you form the aromatic ring, but this is the way the rings are formed in reality. It's really a snake that touches and forms a ring, and then the ring may grow. Strange thing, you are not going to understand it in my course. Maybe if you are chemical engineers, you do that in the next Chemistry 2 course. Strange thing is the first ring that forms is 5. Then it becomes 6, but it's not the first to be formed. Okay. Each one of these 2 families, open or closed cycles, rings, can be saturated or unsaturated. What is the meaning? Saturated, no double or triple bonds. Unsaturated, double or triple bonds are present. The saturated, when have no closed ring, are called alkanes. And when you have closed rings with saturated structure, you have cycloalkanes. When you have the double bonds, you may have alkenes. I don't know really what is the difference in pronunciation of these 2, but one is with 2 and one with 3. And the same holds for the cycloalkenes with the triple bond. Okay? Here you see all the hydrocarbons, only hydrogen and carbon atoms, families. And let's start with the first family, the easiest one, the alkanes. No double or triple bonds. And in this case, a linear chain, an open chain, no rings. Well, these structures are characterized by carbon in the sp3 hybridization. sp3 hybridization. I assume you remember what this means. At the end of the story, it means that carbon has 4 equal bonds going towards the edges of a tetrahedron, sort of pyramid with a triangular base. Methane is like this. When you have 2, you have a single bond in between. A single bond in between the 2 carbon atoms, and you have the ethane. When you have 3, you first, for the first time, you see that you do not have, even if you write them this way easily, you do not have the carbon atoms aligned over a line, because they have angles between the bonds that are not 180 degrees, are much less. So even the normal hydrocarbons linear ones, have a zigzag habit. You see that even more with the butane, that is the alkane with 4 carbon atoms. And the hydrogen atoms as well do go in very precise direction around. These are the full series of names until you get to the 10, the compound characterized by 10 carbon atoms. And you call it decane. I'm not repeating each one of them. You may see if they are linear, like these ones. You may also simplify a bit the way you write them by using this central part, always equal. Have you ever heard about the afro-Cuban rhythm of normal butane? It's like this, huh? It has to be in Italian, because in English it doesn't work, because CH2 is too much, but it's all this CH2 or all this CH2 can be, if they are repeated, you put 1 and then you put 8 number, because it becomes faster to write. Now, in Italian it was even better, because ritmo afro-cubano del normal butano faceva pure rima. Now, it's important to have in mind the prefix. So there is a correspondence between the prefix methane for the alkane, but also you use methanol for the alcohol, methylaldehyde for the, or methanoic acid for the formic acid, for the acid with only 1 carbon atom. So the prefix is directly related to the number of carbon atom. You will use it also for other compounds like that are not alkanes, alcohols, aldehydes. So remember it. Meth is for 1, eth is for 2, prop is for 3, but is for 4, and so forth. When you leave the first 4, you are similar to the numbers used in, I would say, Greek language. Pentadigitos. No Greek people here, I guess. No? No. 1? Yes? No. Nothing. Anyway. Well, in this single sheet, there is condensed the way you use to name the hydrocarbons. As you have seen before, you have possibility to have branches, constitutional isomers, we call them, for an alkane. Look, here we don't have any double bonds, so you have no geometric isomers available. You have just single bonds, but still you may have branches. And you have to use the UPAC nomenclature to name and let people understand what kind of compound of the so many ones you may imagine you are referring to. The first thing you have to do is that you have to point out the longest chain. In this case, it is the one you put there in gray, with a gray background. Actually, in this very case, you may also have pointed out such a chain. But in this case, it was a bit more complicated, because with such a chain, you had a group which was a branch itself. So if you have more than one possibility, you select the longest chain that have only single branches, not ramified or branched branches, I would say. Not trees, but only branches. Okay? Fine. Second part, how long is that chain? 6 carbon atoms. Well, I have to use the X prefix. And is it an alkane? Yes, we are talking about alkanes. So it's going to be an hexane. But what hexane? The normal hexane? No, it has some branches. How to mention them in a proper way? First of all, we have to point them out. We have one branch with only one carbon atom and 3 hydrogen atoms. This is methyl group. Once again, meth is the prefix for one carbon atom. The second is called the ethyl group because it has 2. So we have an hexane that has one methyl and one ethyl groups. Now, the last thing we have to do is to point out where they are located. And then we have pointed out exactly that molecule. In that case, you have to start numbering the carbon atoms of the main chain with progressive numbers. And then the lowest number is the one, you have to select the carbon atom of the main chain that is closer to the first of the branches. So it's not, it's correctly numbered this way, and it is not correct to number it this way. Understand? You have to select this one because it is the closer one to the first branch. And then, when you have the numbers placed, you see that the methyl is attached to the number 2, and the ethyl is attached to the number 3. Now you have everything clear, you just have to express it. And do you say 2-methyl, 3-ethyl hexane, or 3-ethyl, 2-methyl hexane? Well, here you have to select an alphabetical order. Ethyl, as an E, comes first compared to the methyl, which has an M. That is the only reason. If I were there, then I have selected the number of carbon, maybe it's more logical. So I start from number 1, the number, so it's a 2-methyl and 3-ethyl. No, it does not work like this. You have to take all the branches and pile them up according to an alphabetical order of the prefix, ethyl, methyl. And then you put the number of the place where each group is attached to the main line. So this compound is the 3-ethyl, 2-methyl hexane. Okay. This is a simple example. You may have very different examples. Looking like people playing football in this case. In this case, you have, once again, an hexane, 1, 2, 3, 4, 5, 6. Ethyl is here, and you have 2 methyl groups on the number 2. In this case, you say 3-ethyl because E comes before the M. And then you say 2, 2 dimethyl hexane. In this case, you have 3-ethyl, this one, and then you have 2, 3 dimethyl hexane. In this last case, you have the methyl on the 2 and the 4th, second and the 4th, and you say 3-ethyl, 2,4-dimethylhexane. It's sort of a game, but it's the way it works, and it has been defined by the International Bureau of Standardization, like UPAC, that is the regulation board for chemistry, UPAC. Look here, the boiling points of the different alkanes. These are the normal ones, the ones that have a linear chain. It is zigzag, but it is a zigzag, but it's linear. And there is no surprise that this number is increasing as long as these molecules are increasing in length. Let me check. Look at this. Why do I put this line here? Well, it's a bit... Put it here. This is water. Clear? It's 100 degrees as a boiling temperature. Water is small. Oxygen, hydrogen. Small, but with very powerful hydrogen bonds. With these molecules here, the alkanes, you don't have hydrogen bonds. You have little by little piling up dispersive bonds, London forces. But the more you pile them up, the stronger is the intermolecular bond, and at the end you may reach with the heptane, something between the heptane and octane, a number of small bonds, because they are touching, that provides a sort of equal cohesion to the liquid compared to water. So that you have a boiling point that is similar to that of water. There is also the molecular weight that is playing in favor of this molecule, because the larger they are, the less prone they are to go in the gas phase. In case of heptane and octane, the molecular weight is 100 or 114, which is much more than the average molecular weight in the atmosphere. What is the average molecular weight in the atmosphere? You have 4 parts of nitrogen, which is 28. The nitrogen molecule is 2 times 14. And 1 part of oxygen, that is twice 16, 32. Okay? The mixture is about 28.8. So any of these molecules, when moving into the gas phase due to a boiling or an evaporation process, finds himself quite fat. So this helps also in increasing the boiling point. So it's a mixture of these 2 factors. Little by piling up carbon atom after carbon atom to build longer and longer chains, you are increasing the size, and you're also increasing the intermolecular forces between 2 different molecules in the liquid phase. Okay, by this means you may get to boiling points similar to water, but you need much larger molecules. Let me anticipate one thing that we are going to see when we are talking about polymers, and I have already mentioned to you. Polymers may be also hundreds of carbon atoms. We are not talking about a spaghetti, we are talking about the lines to distribute the power. Very long wires at the nanoscale. But they have only London forces. But these London forces are so strong that you have such a performance. This is not like water. This is like a solid. But here you have weak forces. But you have such a long molecules, they are also called macromolecules, that you have materials that behave like a solid. And by the way, they are extremely cheap. This is the power of plastics. Of course, you cannot do, but you know, I've already anticipated to you that they are building airplanes based on plastic composite. So, anyway, let's move on to the second family. Oh no, there is also the combustion as a property of alkanes. This is something that we have learned so well, and the final products are CO2 and water. The second family is the alkenes, and in this case you have a double bond. You need just one, and then you are in the family of alkenes. Just one double bond, and you are no more an alkane. You know why? It's not negligible, because that single double bond is so weaker compared to the single bonds that it dominates the nature and the reactivity of the alkanes compared to the alkanes. Okay. For the carbon atoms that are close to the alkane, to the double bond, you have a different form of hybridization. To have a double bond, the original p orbital of the atoms, and so you have an sp2 hybridization. The suffix is ene, E-N-E. And the prefix is meth, but is 4, this is 1, penta is 5, prop is 3. So you may already understand a bit more of what I've been trying to teach you so far. You may have also in this case linear molecules or branched molecules. This is ethene, and here you have propene. Are they different molecules, this one and this one? Are they different? If you say, yes, they are different, I will ask you, take a mirror and see them through a mirror, you will see that they are changing into each other. They are reacting. No, they are exactly the same. They are really the same. If you put yourself on the other side, they become different, but they are not. For the butene, you may have the double bond also here, so this makes a difference. This makes a difference. For instance, when you have two double bonds, you add to the suffix a D, di or a di, diene means two. In that case, if you have a diene, you have to tell the reader where are these two double bonds located along the chain. In this case, you may say, okay, 1, 2, 3, 4. Is it correct? No. Because you have to start numbering the bonds to tell where are they located from the first of these double bonds, or the first of the carbon-carbon bonds that closer, the carbon-carbon bonds at the extremes of the molecule that is closer to the first of the double bonds. In this case, you have exactly a double bond at one of the extremes of the molecule. So the correct way to number them is 1, 2, 3, 4. Even if it is written the other way around, you have to start numbering the double bonds. Look here. We are not numbering the carbon atoms, because now we are referring to the position of the bonds, the double bonds that are characterizing the alkanes. And you number them 1 and 3, so it's called 1,3-pentadiene. means these numbers are the first one referring to the second carbon atom. 2-methyl means you have a methyl group attached to the second carbon atom. But this second number here refers to the location of the first, of the double bond. Now, this is another, let me clean up a bit. Consider this one. It's a sort of a game. Here you may say, well, it is an ethene, correct? And with one of the carbon atoms, 2 methyl groups. You may call it 1,1-dimethyl ethene. But no, it's not correct. You have to take the longest skeleton chain. And the longest skeleton chain is for sure this one or this one. They are equal. Fine? So it's a 3 carbon atom chain, so it is a propene. It's a 1-propene. Well, if it is a propene and not a diene, in this case it's even impossible, but if it is a propene, then it's obvious that it's 1-propene. If you eliminate this one, it's clear enough. But if you want, you may say it. It's a 1-propene, and then you have to put in front of it the location of the methyl. It's 2-methyl. So it's 2-methyl, 1-propene. Let's move on. And here you see the most gorgeous thing a double bond can do is to open up and allow addition of whatever you want to create. If you want to put hydrogen on it, you create an alkane. It's fine? This is quite popular when you shift from animal grease to something that is not so bad for your blood, cholesterol, things like that. You may start from olive oil in this way and end up with margarine. You understand this? It's a sort of vegetable butter. I don't know, it's vegetable butter. We call it margarine in Italy, but you just start from the oil, you hydrogenate it, and you get a buttery behavior. Another opportunity is if you work under acidic conditions, that is a sort of a catalyst for this reaction, you may add water over the double bond. And the result is that you generate an alcohol. And alcohol is the one that is the organic compound with an hydroxyl group. You may also promote polymerization. A single ethylene can open up and create a long chain, as we do when we make up circles for dancing. This is a sort of polymer of human bodies. They were doing like this, and then they open up the double ring and they embrace each other. And you pile up one after the other. Here you have 3 that have done so. By these means, you create very long molecules that are called polyethylene molecules. And these are polymers. By the way, very cheap and common polymers. Last family, 3 bonds between carbon and carbon. The alkanes, I don't know, with like this. Ethene or acetylene is the smallest one. This is the suffix. Well, you have 2 Greek P bonds. They are more reactive than double bonds. So they are really also unstable. When you have acetylene, you are at the risk of explosion. This is much more dangerous than the alkanes or the alkanes. And, well, it's not really common to have a triple bond involved in organic chemistry. Sometimes it's too unstable to operate. Cyclic hydrocarbons, like the cycloalkanes, can be represented as these ones. Cyclopropane. It's not easy because it's a bit distorting the normal degrees between the bonds of carbon. It's easier here. You see that it's not a square on a flat surface. It's a bit bent, you see. This is because it is sp2 hybridization. sp2, so they have to obey something like this. The most well-known shape is the one of the cyclohexane. And in that case, you may have a boat or a chair. In both cases, you are obeying the sp3 hybridization. So each one of these carbon atoms delivers its bonds towards the edges of a tetrahedron. But the result, it may be a boat or a chair. And they are different. And they have different behaviors, different properties. The last family, and then I stop in a few minutes, is the aromatic compounds. We have already seen these. We have already seen this as a resonance between different shapes. We have seen, in any case, that this aromatic ring is very stable. It has molecular orbitals that are traveling around the entire ring, that are so peculiar. The rings, the benzene rings, can condensate into naphthalene, which is something that you smell if you want to preserve from insects your suits. Anthracene, we are moving closer and closer to the asphalt used for the streets. The compounds are of this type. But you may also have compounds with different elements in the ring, like the furanes, the pyridine. Pyridine has a nitrogen in the ring, or thiophene. Thiophene, that has a sulfur element in the ring. You know what is the main use, for instance, of thiophene? It smells terribly, like many organic sulfur compounds. It is used as an odorizer inside the natural gas that gets to your apartment. In this region, for instance, that is the one used. So it is the odorizer. You feel you have a loss of methane because you smell the small amount, a few parts per million of thiophene that is put there on purpose by the distributor of the natural gas in order to detect leakages. This is the tetrahydrothiophene. Okay, I will stop now. We will use this to go back into the mood and then move forward in this lesson for the second half of this lesson. Tomorrow, 1 o'clock, Aula 1.